So let's see. I'll write some of this down, and then we will go to chapter 6 and see what it was they wanted us to do. We could even go to chapter 7, and they could see what they decided to make this. But let's see. So we're going to do problem 382 right there, and attempt to replicate here. The x direction. And then, see, what is that? That's a 250, and there's a 300, so there's not that much difference. And I didn't do a great job of getting that centered. But it's just for show. So, all right. And that thing's right there. Yeah, not some of my better work. And so one thing I've meant to mention in all of these 3D shafts is these are kind of poorly designed shafts, but we kind of need some of that poor design to try to give us a challenge. Most of the time, you try in a well-designed shaft setup, you would keep the length between components relatively short for this very purpose of trying to avoid bending stresses, right? But we kind of purposely make them unnecessarily long. So we will have so there must be some reason, some practical reason why we were forced to try to have like really long shaft, which I think you could probably, never mind, I won't say that out loud. So this is actually kind of a difficult one to draw. Let's see if I can try to get it so it looks like it's in the right plane right there. So that's that angle right in there. Or I guess they made it this angle right in there. So let me erase that vertical line because we got it in the way. So that's 45 degrees right here. And this is the 300 newtons. And this is only 45 newtons, okay. And that, no, I got that one away. Oh boy, didn't do a great job on this. 150 millimeters. It's there. Break that off there. 400 millimeters. This is 300 millimeters. This diameter, there's my own way of writing it, like that right there then. 250 millimeters diameter. This is 300 millimeters diameter. And this is T1 and T2. I hate it when they do that. And this, for the time being, is 20 millimeters. Diameter. Did you get it, everybody? Sure. And then I think in this problem, this is 382. 382. They did the 15%, right? So the belt tension on the loose side is 15% of on the tight side. So, okay. So I also said that I wanted to see what they wanted us to do in chapter 6 with this problem, make it into a fatigue problem. So that was problem 382. All right, looking through here, that's like, for the problem specified in the table, build upon the original problem to determine the minimum factor of safety of fatigue based on infinite life using the Goodman criteria. The shaft rotates with a constant speed and has a constant diameter and is made from AI SI 1018. All right, so that's what we'll have. AISI 1018. I said 1018, right? Not 1080. That would make sense. 1018. So that's that one. So that this would actually also be, let me see, I'll write that down just for the record. That's problem 640 out of the 11th edition. And then I'm just curious, while we're looking at problems, let's take a look at the 7th, chapter 7, and see if there's any reference to that. No, they didn't do it. I didn't see it. This is going to be like redesign. Oh yeah, here you go. For the problem in the specified table, build upon the results to obtain preliminary design of the shaft by performing the following. Sketch the shaft general layout, including means to locate the components. Okay, so that means that they want a stepped shaft. To transmit the torque. Okay, so that's also, you need to put a key in there. Estimates for component widths are applicable at this point. Okay, specify suitable material for the shaft. So there's definitely a design going on here. Determine the critical locations with a design factor of 1.5. Check and then check for yielding. Make any other dimensional decisions necessary as specified right here. And then so you can see that one goes down to so this was 382. So this is technically problem 715. And I think in the solution manual for this thing, they don't bother giving you an answer because they said, because they were lazy, because they said, oh, well, you know, your mileage may vary. While we have the book out, let's take a look at 1018 and AISI 1018. Should be this guy right here. We're in metric. And they didn't say, I didn't write that. Did you know if it was cold drawn? We'll go back. Problem 640. Hot rolled, it's probably cold drawn. Yeah. I hear you. So, cold drawn. Thank you. So, 1018 cold drawn. And in metric, so we have a yield strength SY of 370 megapascals, and we have an ultimate of 440. And I think this was 0, A, B, and C. All right, so getting pretty used to this now. Let's come in and do some preliminaries. Let's find out what these T's are right here. So I think this one's bigger than that one. We'll kind of make it look like this, and this is going to come up that direction, and these are going to go that direction. So this is T1, T2. Here's the shaft center, and this is 45 newtons and 300 newtons, and that angle is 45. Doesn't matter here, so we'll just go. Sum of the moments about the x is equal to 0. Z, this is y. Let me write this out. All right, so well, we could just look at this and see which one's going to be the one with the larger tension. This is making it go counterclockwise, therefore this one must be larger to make it go clockwise to balance them out. So T2 is going to be equal to 0.15 T1. So when we come down to here, and we could cheat a little bit and say, okay, this is going counterclockwise, so it's going to be 300 minus 45. It's just a small cheat, right? We know they're opposite, so that's going to be times the radius of the smaller one, which was 250. We don't have to actually make it a radius because we're about to, just find out what this unknown force is going to be. So in this one, it's going to be let's see, I made it negative, so it's going to be this one going clockwise, so it's going to be T1, but it's going to be minus 0.15 T1. And that's going to be the 300 over 2 and equal to 0. Get rid of that. At least I get rid of that. At least. And so, T1, math. I should be able to do that in my head. 255? Sure. 255 times 250. Is that true? Okay, cool. And then divided by, and then divided by 0.85. So I think we should get 250 newtons. And this would be 37.5 newtons. We're okay with that? I jumped a couple things, so I always chance I made a mistake. We could go either one of these. We need the torque. I don't like tension. Can I change all that? I don't like writing T for things. We use T for torque. Yeah, it's a lot of hoopla. I go FT1, FT2. All right, so FT. I don't have to change all of them. In fact, we could just do that right there. Right? FT. Whatever. I left that one. I go FT1. FT1. Okay, that's actually would have been easier. Let's go back to this. Okay, so we'll do another one. Sum of the moments about the x equals 0. Well, I should draw it over here somewhere. It doesn't matter which one we do. So let's do this one. 45 newtons and 300 newtons. And so that's going counterclockwise, so this must be going clockwise. So we cut the shaft right in between the two. That's where the torque is located. So we'll say that we have this, once again, 300 minus 45. Here is where you got to make sure we get the units right. This is actually 0.25 divided by 2. And then this is minus T. Equals 0, so we have a torque. So at 255 times 0.125, we have a torque of a whole, doesn't seem like a lot, 31.88 Newton meters.
Question.
Yes, sir.
So we can just not apply like cosine or sine for the relationship on the we were finding the moment.
Yes, because these are tangent to the thingy.
Okay.
Yeah. So all we need is the radius. Here's what we're going to need to do for the next part of the thing. When we go to do the shear moment diagrams, we do need to break these into into y and z components. That 300 and that right there. So I think, as I recall doing these before, I used to write that out over here to the side just to. So I could just, this is me just, because I like to write things out. And maybe I should have done it on top of this right here. But if this was the 45 and this is the 300 and these are both 45 degrees, I would say the 45 cosine, it doesn't matter which ones you do, you'd have 31.82 and 31.82, and then you're going to have 300 times 45. Let's say cosine. So you get 212.1, 212.1. So the total of the thing coming this way and that way is going to be 240, let's call it 44 newtons, and 244 newtons here. All right. So when we go to draw this out right here, I'll make it small. And we go up to here. There's not much of a distance right there, right? Try to make it similar. I think this is going to be up 244, and this is also going to be that direction, right? Because this is Y, this is X, that is Z though, looking downwards onto the thing, and this is X. So this is going to be 244. And this is going to be the combined of what we found up above, like 250 plus 37.5. So was that 287.5? Didn't do a great job with that one. And these distances are 300, 400, 150, 300, 400. I guess I didn't draw the scale, 150. And that reaction's definitely down that way, and this reaction here, so here's going to be R-O-Y, Roy, and he's going to be R-C-Y. This one you can't really tell which way it's going to go. These are fairly close values to each other. I'm pretty sure, pretty confident we're going to have our R-C-Z in that, over that way. This one, not quite so sure, probably. I'm going to guess. That's the direction. So this one pretty easy to do. Let's see, here's the moment diagram here. So I get the sum of the moments about the about O in we can say it's OZ if we want to, because it is about the rotating the Z, equal to 0. So we have 244 times, I'll keep them as millimeters, 300, and then minus RCY, and that's what, so 700, 850. So 244, 300 times 850 divided, we have 86.12. This is a pretty small number. So I guess the most of it's going to be over here at ROY. Yeah, that makes sense because this is 550 and that's only 300. Okay, so sum of the forces in the Y direction equals 0, coming up. And we'll go negative ROY plus 244 minus 86.12 equals 0. So we got ourselves an ROY. 244 minus, okay, so 157.9 newtons. And then come back over here, do the same thing. Goes some of the moments at O about the y-axis, and now we got a little bit more things to do. We got 244 times 300 minus 287.5 times 700, and then plus RCZ times 850 equals 0. And 244, 300 times, and then 287.5, 700 times, subtract it. That brings it up to the other side. Sure. And then just 850. 850. So we get RCZ is equal to 150.7 newtons. Sum of the forces in the Z direction, positive is down. We'll take ROZ minus 244 plus 287.5 minus 150.7 equals 0. Here's, I gotta check my directions really closely because I can't be 100% certain which direction that's gonna go. It would be possible to make it 0, but that would be unlikely. Okay, so I'm gonna go 244 here, 287.5, add. That jumps over. Okay, sure enough. Okay, so that was the right direction, so you get 107.2 newtons. So we go ahead and put this in here, and Roy is 157 downwards. And this better come up to right here, all the way across. 157 is a negative 157.9. Put the newtons in there. Here's M. So these are Newton meters. And then this better be 86.12 if you add that and that together. It better be equal to that. This is going to come down to here. Over here, so we should find these two values right there. So right here is going to be 0.3 times it. So this should be a negative 47.37. And this one coming the other way should be 86.12 times 0.15. So it has a relatively small 12. It's also negative 12.92. We made this pretty small. We might want, this figure small because if we do the chapter 7 stuff, we actually want to try to go to figure out what a typical width might be for this gear. We'll just kind of have to guesstimate based on its proportions and find out what the moments are going to be right here and right here to either side. Because we were going to do a step shaft, so we have to kind of actually. We could just be lazy and say, okay, and be a little conservative and just go ahead and use that moment to each side of the thing. And the same thing true with here. But let's go back and finish this one up. So we have 107 going this way. And then we're going to go up. So it's 107.2, 244, subtract out. We're going to get negative 136.8. and then we're going to go down, so we're going to add 287.5, and it should come out to the same 150.7, and it sure does. So we're going to come down here and a little bit lower. I'm going to try to draw that out. So that's going to be 150.7, and so here we're going to come down this amount right here, and once again I should have maybe given myself some more room, and I made it look like a curve. Bless you. Bless you? I just said bless you to myself. This should be a straight line. I might like just try to be a little bit. I'll make it a little smaller. There you go. So 107.2 times 0.3, we're going to have 32.16 right here. Now we have 136.8 times 0.4, boom, and we're going to subtract that. So we end up with a negative 22.56. So that's going to be up here. It's going to cross, and then it should be, if we go ahead and multiply 150.7 times 0.15. So let me try that out. I'm just going to go, so I already have it in my calculator right there as one. I'm just going to multiply it by 0.15. Yep, and it comes out to damn close, right? So it comes out to, this right here is negative 22.56, and if you multiply this, I get 22.6. So it's got to come out to 0 right here at the end. It's kind of a little bit of a weird looking guy. All right, so let's get rid of the clipboard. Don't need it for any reason. And continue on, and we'll need to find the maximum moment there from this. So the moment at A, right, because remember that's O, A, B, C, O, A, B, C, is going to be the square root of negative 47.36 squared plus 32.16 squared. So 47.37 squared, 32.16 squared plus square root 57.26 Newton meters, and then MB is going to be this diminutive 12.92 squared plus the negative 22.56. So this could be smaller right here, and so 12.92 squared and 22.56 squared plus square root, so we get 20, basically 26 Newton meters. So it's 25.998. And now, so this is the maximum, so we're going to go at A, and so we'll find what the bending stress is going to be. We can go with, we'll go with the easier way to do 32 m over pi d cubed. So 32, and we have 57.26 pi, and then the diameter of the shaft is 0.02 cubed. So 32 times that, pi divided, and then 0.02, 3, raise it, divide it, and we get 2.27 e to the 7, so that's 72.9 megapascals. the torsion is 16t over pi d cubed. So 16, and the torque was 31.88. Pi is and then 0.02 cubed, and so we go 31.88, and pi, whoops, what did I just do? Okay, losing it, sorry. My brain turned off for a second. Happens. I get 20 point, call it 30 megapascals. I don't know why I have so many sig figs there. And now we have, we want to let's just check this right here, von Mises, just because it's right there, right sitting there for us. Doesn't matter. 3 tau, I'm not going to bother with a subscript. (72.90) squared plus 20.3. This would be a 20. And there should be a 3 right there. This kind of stuff I mess up all the time. I get 80.93. So this is not a lot compared to our yield strength and ultimate. Let's keep proceeding. It's probably going to pass. Right, already passed yield. We could go now and go to endurance strength. We could do this in one step right here. So Ka, Kb, Kc, Kd, Ke, Se prime. All right, so we know the Se prime is going to be 220, right? It's just 0.5 times that. We go through these others. Don't have to spend, you know, we go pretty fast through them. Once we get used to them. One of the benefits of practicing problems is also that you get, during exams, you just fly through the things. So our Ka, we're going to do the surface factor. We said that was cold drawn. Also, this is something that's typically machined, so we use this one a lot, right? The machined or cold drawn, it happened a lot right here. And for the factor using SI is going to be 3.04 for the A and negative 0.217 for the B, used inside this equation, equation 618. So A SUT to the B, and that ends up being 3.04, 440. This equation is made for megapascals, so we just put in megapascals. 0.217. So we go 440, 0.217, make it negative, raise it and multiply it. Boom. 0.8114. And I had a student one time always messing these other things up, and they'd get some crazy ass answer, and then they would just go with it. You know that it's got to be somewhere close to 1. So don't write 0.100003. You know, just don't do it. You know, just anyway. Couldn't convince them. That's right. All right. So this is a rotating cycle. So we don't have to do any adjustment for it when it comes to this portion over here, right? So if it was a circle that was not rotating, we would actually find the equivalent diameter. We don't have to do that because it is rotating. So we'll just use the diameter, and it is 20 millimeters, so it falls in this category. So we'll use 1.24 times the diameter raised to the negative 0.107. So it's going to be 1.24 times the diameter. I'm just going to go ahead and put the diameter there, 0.02. Oh, excuse me, I'm sorry. This, okay, now if you get a weird number, if I had just done that, and I got a weird number, I'm like, what the hell did I do? This thing is meant for millimeters already. So you need to put the millimeters in there. So sorry, 20 to the, I turned my brain off for a second. That's the plug in chug mentality. Is just turn your brain off and put numbers inside things without thinking. Don't do that. Don't be like me, kids. I said kids because it was a funnier thing to say, not that I'm calling you kids. Just keep talking. I got 0.89999. That's 0.9. I guess I could put it in. That's 4 sig figs, right? Sure. 99994. Not a lot. KC is going to be equal to, I believe it's going to be equal to 1 because it is bending. This is the load factor. You know, we're doing apples to apples things here, so we're trying to adjust this endurance strength so it is closer to our situation. Nobody mentioned anything about temperature, so our temperature factor is going to be equal to 1. It's funny, they used, in some of the other editions, they have an equation for this. I mean, they have a table for this, but here they have an equation. And I think they have a different equation in the 10th edition, so there you go. There's that. And then nobody said anything about reliability. So the KD, that's the temperature one, the KE is reliability. And as I mentioned, I might ask you a question on the exam, and if there's no mention of a fully corrected endurance factor, you'll have to go through this. But if I give you an SE is equal to the fully corrected endurance, you don't have to go through this process, so don't waste your time doing it. If I ask it, I'll only ask it once. I won't ask you to do it multiple times. It would be a waste of time. Just want you to demonstrate you could do it, or that you recognize that you should do it. So sticking this back in here, SE is going to be equal to 0.8114, 0.8999, 1, 1, 1. I think I got all those right. That 1, 2, 3, 4, 5. Yep. And then I'll take my 440 and divide it by 2, or I could multiply by 0.5. I'm doing the same thing. Boom. So 220. Boom. So we have 160.7, call it, megapascals is our endurance strength. So if we're going to go by the Goodman criteria, we have enough information available to us. And let's see, we will go N Goodman is equal to 1 over alternating. Should I do that? Yeah. Oh, something I should do first. I'm sorry. My bad. I should turn these into von Mises stress. So I guess I will. I need alternating. Well, what is alternating? Alternating is going to be the von Mises for the, so let's say here's the alternating von Mises, square root of the alternating this plus 3 times the tau alternating here. But the torque is not, so we're taking the square root of the square of the von Mises, so the alternating is just the bending. So it is the 72.90 megapascals. And the mid-range is the square root of the mid-range normal stress plus 3 times the mid-range squared. So there is none of this, but we do have to take this, right? So what we really need to do is take the square root of 3 and multiply it by 20.30. Does that make sense why we did that? Because we were going to square this and then take the square root of it. So all we had to do is a 20.33 square root times, and so this becomes 35.16 megapascals. And so now the Goodman, we'll write it out, 1 over sigma A prime over SE, that's the alternating, plus sigma mid-range divided by the ultimate. So 1 over 72.90 divided by 160.7 plus 35.16 divided by 440. And so did I ever do, sure, 72.9, and then swap that out to 440 divided plus, and then 1 over. And I get a 1.87 is my safety factor. Fatigue safety factor, and that shows that we have, this is the margin that it has, and so we're predicting infinite life, and then here is the margin we have beyond infinite life. All right, so if we want to go for the design side now, we have to make some choices, right? So that's at the worst location. Let's go backwards and see, well, can we make it smaller? What is the minimum size that we would need to make? All right, so here's my design scenario. What is the minimum size that we would need to make over here and have the same safety factor? Right, so that we picked the worst spot. We established it was the worst spot over here, but now we have the maximum moment that we have at B. And we're going to have the same torque because it's to the inside, so like right in here is where we're going to look. And let's see how small we can go ahead and make it and get the same safety factor. Because if we use the same diameter all the way through, that's kind of a waste. We don't need that. We need this diameter right here because we have this larger moment. Significantly larger. Let's see how much smaller we can make it and save some amount. It's not going to be a lot because it's only 150 millimeters long, but I'm just coming up with a design scenario right here. So we go to chapter 7. Now, one of the things we have to remember is that we use this for our SE. So maybe later on we want to be really, really, accurate. We would when we find a diameter, we'd go back and we would update this. But right now that's just going to be a preliminary estimate because there is some amount of circular logic going on right there. They're like, oh, we needed this so we could design it to find out that. And we don't have any stress concentrations yet, so that's another cycle that we might go through. Is we might okay, now we're going to put a step into it because we're going to pick another diameter. So just recognize that as we go through. That's one of the reasons why it's nice to do the things in Excel, because you could you go through the preliminary, find a thing, then update it and try it again. All right, so if we're going to use what's in here, okay, so we're going to take we do know there's going to be a step, so let's go ahead and take a step. All right, so this is stuff that we're doing in the next class. We should have done it yesterday, but I talked about too many things to get. But we introduced it. We just didn't do an example with it. So we're going to be ahead of the game. So we're going to need a KF and a KS. Here's our calculations right here. So let me write down these equations while we have it right here in the board. So here's going to be design. Design min diameter. That's supposed to be diameter at B to have same n good as A. That's our design. So we start out with our KT, sorry, and we're going to say there's a step there. We could, let's just go with a keyway. We have to have a keyway anyway. We probably should have had that over there, but we're just doing it as an example, so we'll just go with keyway. Keyway, and at the KT for bending, and then there's a KTS for, let's see, is it before or after this? Or there's a KTS for the torsion, or just drop it there if you want to. Yeah, right here. All right, so we go to this table, and we'll find the KT, and we're just going to use it, I guess, maybe. Let's, whatever. And we have an end mill key seat. We have a sled runner key seat, but they don't give us the other piece of information here, so screw them. We'll just go ahead and use this one because they have it. So 2.14 for bending and 3 for torsion. That's going to mess us all up, actually, because we didn't use it for the other. So it might, we could have a scenario where we end up getting a larger diameter. I'm going to decide, I'm going to make a call. Okay, we're going to ignore stress concentration. For now. So I just want to make a compare. So let me go back to the equation I meant to write down, which was going to be that A, and this is the 11th edition, they don't have this in the 10th edition, it's going to be the square root of 4 times KFMA squared plus 3 times KF TA squared. Is that right? Okay. And then B is going to be equal to the square root of 4 KFMM squared plus 3 times KF TM squared. All right, so one thing we don't really care about we don't have an alternating torque. That torque is constant. We don't have a mid-range moment. That moment is always alternating. That's happening right there. And we are assuming KF is equal to 1. So we could take a square root of 4 times the mid-range, which we just said was going to be 26. And squared. So I kind of preferred to have this in the other thing, but that's all right. We'll survive. 26 squared times 4 square root. So this is 52 whatevers. I guess this still is a Newton meter, isn't it? Yeah. Those are all constants. But I'll just leave it without a thing. And then this one's going to be the square root of 3 times our torque, which I think was 31.88. So 31.88 squared, nope, 31.88, losing it, squared 3 times square root. Could have just multiplied it by square root of 3, couldn't it? 55.22. And now I can plug that into the equation we have for Goodman for this right here, right? So there's the diameter equation. I'll write it down onto here. Diameter is going to be 16 n over pi, and then have A over SE plus B over SUT, and take the 1/3 of it. Now, I'll go ahead and put this in as 1.87. So that's 16 times 1.87 pi, and I'll go 52 over endurance strength of 160.7 plus 55.22 over 440. The ultimate strength raised to the 1/3. And we're going to expect this to be in meters, right, in our units. Because we have all, oh, wait. I might want to be careful here. These should be Newton. Oh, okay. So I should, when we were done, I was going to screw something up here. E to the 6. E to the 6. If you get a weird answer, got to go backwards. Right? Is that true? Yes, these are Newton meters from up here. So this needs to be in terms of newtons per square meter to be able to get out what we want. And so what's going to happen right here, notice this is Newton meters, and this is newtons per square meter. So the newtons will cancel each other out, and the square meters, there's a per, so it's going to come up to the top. It's going to be cubic meters, and we're taking the cube of them. Man, units will burn you. So watch out. So we get, 52 divided by 160.7 E6 divide. And then we'll go 55.22 and have 440 E6 divide. Add them together, multiply it by 16, multiply by 1.87, and divide by pi, and then take the cube root. Boom. I get 0.01623 meters. Therefore, that's going to be 16.23 millimeters compared to the 20. So I'm glad I didn't put the stress concentration on there, because that would have not been a good comparison to the other ones. The other spot didn't factor in stress concentration. So when calculating this as a means of comparison. But of course, 16.23 millimeters is a weird size. So we want to go to our table A17 in the book and see what, this is just some guidance, right? This is the only guidance we have. This isn't the Bible. You don't have to stick with this. You could pick 17, but it probably isn't in here. For millimeters, is it typically acceptable? Yeah, 18 is in there. So I think 18 is the best choice. Of course, look at that. Does it matter? We only saved 2 millimeters. Makes sense, pick 20 millimeters across the whole thing, right? Wouldn't make sense to have switch from, you're not saving anything. So, my conclusion, and then you don't have to do anything with stress concentration factors, right? So you just find some way to have to keep that position of those pulleys exactly where you want it. There's other ways to, besides a key way and a step to put to make sure the thing's in the correct place. You could, not a great idea in some instances, but it is done, is to have a hub on the pulley and then put a pin in it. My problem with that is if you design it ahead of time and you buy a pulley that has a hole in it in the hub, and before you get it there, you drill a hole into the shaft, it's really, really tough to get those to line up. So like what they will often do is they'll put it in a place, make sure it's not wiggling around, and then drill the hole through the shaft with the pulley in place. So you make sure that you're getting that, and that, instead of trying to drill it, because you can imagine if you were to, when you go to drill something, you have to drill exactly on that spot, directly through the center. And it is tough not to get that off by a little bit, just to get it off. And you know, in terms of just old school machining, right? We might be able to CNC thing, but that's like kind of overkill to drill a hole to CNC into a shaft.
Do it on a drill press.
Yeah, to do it on a drill press, but to get it exactly right, you can imagine that the thing like we'll draw the cross section of the hub right here, and it comes pre-drilled right here, but you drilled it off a little bit. Now you got to get that pin in there, but not to mention it has to go all the way through, right? So you're not going to get the size. You're not going to be able to get the size pin that you want to be able to do that. You're going to put some serious loads into it. It might be close enough where you know where this, you know, you might be get a hammer, make that thing fit into place. But if you're doing like if you're doing precision work, right? This is a terrible way, but it gets done. It's done that way all the time. But you just recognize that that is potentially an issue that you would have in there. It's also the shearing of this piece. Maybe if you don't got to worry that there's always going to be tolerances that would need to be in place to allow you to do that. And those tolerances could make for a looseness, or it could also make for a stress that you're putting into the piece. You could be stressing the hub because you're trying to force a pin into misaligned holes. These are considerations to, you know, in your decisions, your selection of how you're going to secure this in place, decisions on what, you know, is this a high quality piece of equipment that's supposed to last a really long time in a critical use, and what are the consequences of it breaking when in operation? Like, will human life, you know, so, you know, or is this just, you know, going to be used in a barn every now and then, right? And if it breaks, you drop a bale of hay. Who gives a shit, right? It's the design has to come into play. All right, so there's a problem we worked pretty much all the way out to a conclusion and built upon some of the stuff we talked about. All right. Woohoo, 205.